All right, can you all hear me well? Okay, thank you. Welcome to my education session today. I'm going to talk about challenges and opportunities in gas flow measurement and ventilator testing. Thank you so much for attending this session. Really glad to have you all here. Before lunch here, my name is Daniel Benz. I'm the managing director of IMT.Analytics US Sales and Service in St. Petersburg in Florida. I'm originally from Switzerland, but I've been living in Florida for the last year and a half. Me originally being from Switzerland means there are some good and bad news for you. So the bad news is for the next hour you have to deal with my strange German accent. But the good news is I've recently been back in Switzerland and I brought some imported Swiss chocolate for you guys. Please pass it around and enjoy some. It should be a bit of an energy kick and an energy bridge until lunch. All right, so it's really from Switzerland. It's not like produced locally. So hope you enjoy it. So in the meantime, a little bit more about myself. I'm an engineer by training. I've been working in the medical devices field for 12 years. Held different roles, mainly in tech support and technical training for ventilators, and also in customer service and now management for both ventilator manufacturer and now with the test equipment manufacturers, IMT.Analytics. So before we start, I just would like to know a little bit about you. Who of you is currently involved in ventilator testing and anesthesia machine testing? Please raise your hand. All right. How about people who have never worked on a ventilator or anesthesia machine so far? Okay, good. You have a fairly good mix, I think, here. Particularly for those of you that are new to the topic, if some things are a little bit over your head, or if actually for all of you, if you have any questions at any time, please feel free to raise your hand or just shout out. I'm happy to answer questions at any time. Don't wait until the end of the session. It would be great if this is a little bit interactive. So really, don't hesitate to interrupt me if you have any questions or if something doesn't make sense to you. All right, so as I mentioned, I spent most of my time, my career in the medical device industry in tech support and technical training for ventilators. Same applies for some of my colleagues at IMT.Analytics. So we've all personally faced the challenges in gas flow measurement and ventilator testing. So the things we are gonna talk about today are not kind of made up stories. These are things we have experienced ourselves or things that came to us through tech support requests or what we heard in classrooms. So I hope this is all gonna be helpful for you guys, and we're gonna try to support you with the basic knowledge so that you can better understand how it works and to overcome these challenges in the field. While doing so, I'll keep this very generic. I'm not gonna talk about any specific brands or models, because really the aim of this education session is that we build your knowledge about the topic. And of course, we'll show you how state-of-the-art equipment is gonna help you overcome these challenges, but it's not about specific brands or models. My aim is that you all learn something new today, all right? Okay, so what are the challenges we are going to discuss? So of course, there are many challenges out there, but the three challenges we think are the most frequent ones we see in the field is, the first one is that we have complex and sometimes unclear measurement setups. The second one we are going to talk about is ensuring that your gas flow analyzer is set up correctly. There are many settings on gas flow analyzers which are very important to be correct for accurate measurements. And then the third challenge I'm going to talk about is understanding the test sequence and valid ranges defined by the manufacturer. So for each of these challenges, we are going to dive deep into kind of basic knowledge and then see how we can overcome them. Mainly, we're going to spend time on the second challenge. That's the most important from our point of view and the one that needs the most explanation of background knowledge. So once again, let me know if you have any questions. Just feel free to interrupt me. All right, let's dive into the first challenge, which is complex and unclear measurement setups. So what we see very often is that ventilator manufacturers in their service manual, when they explain how we have to set up our test equipment and our test setup, this is sometimes not very clear and not very supported by pictures. And if it is, then mostly it's just based on one specific model or brand they've once selected, maybe, I don't know, 10, 15 years ago, right? So here is an example for that. These are two measurement setups from a service manual of a ventilator. You can see they're actually quite good pictures. So they did a good job in explaining the setup here, even though, for example, if you look very closely, there is a teed-in pressure line here, which is very hard to see if you don't know that, but it is important because otherwise this specific model of gas flow analyzer is not going to compensate for the pressure in your flow measurement. So even though they did a pretty good job here with supporting pictures, the complexity of this setup is based on that specific model of gas flow analyzer. It has a lot of different modules. There's a user interface, a measurement module, then you have the T-in pressure, then you have a cable here, you have a trigger cable. Over here, you also have where you need to measure oxygen, then you need to tee in an oxygen analyzer. So everything is, I'm not saying that this is a bad analyzer, this is a very good analyzer actually, and one that is very often used in the field. But the whole complexity of this setup is just based on this one analyzer they are showing you. So what if you want to use a different analyzer? So then you need to figure it out yourself, right? There's absolutely no help from the manufacturer how to set up your measurement setup. Second example here, quite similar story. Again, our picture that we have here is based on just one specific model. And it's not very clear here. We need to connect here the circuit to our analyzer, but which port? There are different ports here, right? And again, if you, for example, use the analyzer that we've seen in the previous example, then if you want to use that one, you probably need to tee in pressure, you need the oxygen analyzer, so you need to know how to set it up for that specific model. So again, here, you see there is some help, but not very in detail, right? Third example, this is a really nice one. Here, the manufacturer just says, tee in a calibrated flow analyzer that can measure tidal volume, and everything else, they leave it up to you to figure it out yourself. Right, so that's not very supportive, of course. So, of course, we can't expect all the manufacturers to show pictures for each and every flow analyzer which is out there in the field, right? And that's why it is very important for you that you understand your gas flow analyzer, right? There are many different models out there, so you need to understand what is being measured, how the parameters are being measured, and then very often you have setup information in also in these user manuals of these gas flow analyzers, because depending on the analyzer you use, for example, the setup we've seen earlier in this picture could look like this for a different analyzer, right? So some analyzers have a lot of different components, some analyzers have very few of them. So it's important that you understand what, for example, your flow analyzer is measuring inside the main flow channel and what needs to be measured with additional modules. The opportunity for manufacturers is to design products that make it easier for setups, right? And one thing that we recommend always, if you select a gas flow analyzer maybe in the future, watch out for what we call all-in-one devices. There are devices out there that actually measure pretty much everything inside just the flow channel. So devices like that, you just connect actually the ventilator with the white piece on one side and then the test lung on the other side, and everything else like oxygen, pressure, temperature of the gas, everything that is needed is then being measured inside that one flow channel. And of course, this helps minimizing the risk of measurement errors caused by setup failures or inappropriate setups. So key takeaway here is just make sure that you understand how your gas flow analyzer works so that you can understand if you see a set of pictures of a different one, how does that translate actually to the gas flow analyzer you're using. All right, any questions so far about the setups? Then let's talk about the settings. So once you have your setup of your analyzer, next thing you want to make sure is that all the settings are correct. And we're going to spend a little bit more time on this topic because there's a lot of background knowledge. Of course, at the end of the day, it will be just a couple of key takeaways we'll talk about, but I also want to give you some background information to understand what we are actually setting up, because that helps you remember why it is important later on. So what are typical settings on gas flow analyzers? So the most important critical settings are gas type. Maybe you've heard about that. Gas standard. These two are actually crucial for all flow and volume measurements. And we'll talk about them in just a bit. Then maybe you've heard about trigger settings. Trigger settings is something different. They are used when we want to measure so-called breath-based parameters, such as PEEP pressure, you'll hear, or a respiratory rate, or tidal volumes of a ventilator. And then the last settings we are going to talk about is the measurement parameters themselves. So gas flow analyzers can measure many different parameters, and it's important that we understand, okay, which parameter do we have to look at? What does it mean on the ventilator? And it's also important that we have it set up, for example, in the right unit of measurement that matches the ventilator. Okay, first we're going to dive a little bit deeper in topic of gas type and gas standard. So why do we need to set a gas type and gas standard on our analyzer? So the main reason is because volume occupied by a gas depends on several factors. So let's say we can capture a portion of room air here in a container with a movable lid up here. And let's call that volume 0. So I have this volume of air in my container, and what happens if I heat up that air, that volume of air inside the container? Exactly, it expands, right? And it occupies a greater volume. Right? You know what happens if we add humidity to the gas? It expands as well. Not to the same extent, but it expands, it still expands. What happens on the other hand if we compress, if you put pressure on the gas? It compresses, right? It occupies less volume. By the way, what happens to the temperature if we compress it? It goes up, right? So some of these things are even interconnected, right? And as a last example here, this is all about gas condition, but it also depends what gas it is. For example, room air has how many percentage of oxygen in there? Yeah, about 21, yeah, 20.8 something, right? So what happens if we increase oxygen concentration of that volume of air? Then it expands as well. So this means that the same amount of gas molecules occupy a different volume depending on gas conditions and gas characteristics. Okay, so that's important to understand later why we need to set gas type and gas standard on our ventilators. Test. Does it make sense so far? All right. So because of that, gas flow analyzers typically need to know a lot of different parameters to be able to calculate the flow rate or a volume. Volume is just flow over time, right? The first three of them on the list here is gas density, viscosity, and a viscosity coefficient. This is typically handled in gas flow analysis by a setting called gas type. So we don't have to tell it exactly this is that density and that's viscosity. There's a preset of different gases that we typically want to measure. For example, air and air-oxygen mixture or CO2, right? And then we can just select from a list the gas type, and then the analyzer knows, oh, okay, this is what we actually want to measure. And this means it knows the characteristics of that gas. And all the other things are typically measured by the gas flow analyzer. So there's something to be measured actually. In our example here, this is for differential pressure measurement, gas flow analysis. There are other principles out there, but typically you have something that actually determines the flow rate itself, but then you also need to know the gas pressure, gas temperature, humidity, and also very typically the concentration of oxygen. And these are all things that are typically being measured by the gas flow analyzer. So we have a setting and we have measurements, and all that actually combined lets the gas flow analyzer calculate the flow rate of the gas that is actually passing through the gas flow analyzer. And let's consider this gas flow measurement. Okay, so we always measure the actual conditions. So to understand what a gas standard means, we need first to understand the separation between gas flow measurement and gas flow displaying. So measurement, gas flow measurement is always based on the actual conditions. We call this gas standard ATP, which stands for actual pressure and temperature. Have you ever heard about ATP? That's one typical gas standard setting on your analyzer. But then with mathematics,
same thing, or is it going to be a different setting?
That would be a different setting. So ATP means just this is the actual condition of the gas that is being measured. Yeah, exactly. So my flow is going to be a little bit different depending on my actual conditions. But then we can, in order to standardize or compare flow rates, we can then calculate them, convert them into different gas standards. So how much of flow would that be, for example, if my temperature would be that many Fahrenheit and the humidity would be a different humidity than my actual humidity of the gas that I measure right now. So this is all convertible mathematically with some formulas in the background. So for now, let's just make sure that we understand this process is called, or we call that gas flow displaying. So it's different what we measure and what we finally display on our gas flow analyzer. So that was now the background. So now you might ask, why the hell do we need to care about that, right? So the important thing, so now I'm going to talk about practical examples. So I think that will make it much clearer. So what you can see here on the screen is a typical setup of a ventilator on a patient, right? So we have the ventilator here. We have an inspiratory limb, typically with a heated and humidified inspiration limb. So we have a humidifier, and usually you have like a heated wire inside your limb here to the Y piece, and then we have the interface to the patient, and then we have an expiratory limb back to the ventilator, right? So let's consider that this ventilator delivers a volume of 500 milliliters to the circuit system. And let's assume that this is dry air from a compressor, like around 5% humidified, and has a temperature of 21 degrees Celsius, so kind of room air, right? So what happens to that volume here when it travels along the inspiratory limb until it reaches the patient? Correct. So first of all, the gas temperature and humidity is going to increase because we have that humidifier and the heated wire here, right? And as a consequence, as we learned earlier, the volume is going to increase, right? So that means the volume that actually reaches the patient is no longer the 500 milliliters that the ventilator has actually delivered to the circuit system, but it's considering that typically you want to have the temperature at 37 degrees Celsius. That's the body temperature, typical body temperature, and it's going to be about 100% humidified. So if we consider that, then our volume is going to be something around 560 milliliters, and not the 500 milliliters that the ventilator delivered to the circuit system. Okay, so, and because of that, what ventilator manufacturers typically do in their settings and the monitoring on the ventilator, they compensate for that. So in such a situation, typically you would then see the setting on the ventilator is not the 500 milliliter that it delivers to the circuit system, but the 560 milliliters that are going to end up at the patient, right? And as we've learned earlier, because that's all calculated, that can all be calculated by gas standard conversion. So this situation is very typical for like ICU ventilators, because 37 degrees, as I already mentioned, and 100% humidification, this is typically what we want to have on the patient side. And this is also called the body temperature and pressure saturated. So the gas standard that many ventilators are using is called BTPS. I'm pretty sure you've heard about that, right? So that stands for body temperature, pressure saturated. Okay? Does that make sense so far? All right, so what is the problem here? When we test such kind of a ventilator with our gas flow analyzer, our setup typically looks like that, right? You just have a circuit system, then we have an analyzer, a test lung, and then in such a situation, it can easily happen that you set up a tidal volume of 560 milliliters on your ventilator, and then you measure with your analyzer, oh, just 500 milliliters. What's wrong here, right? Yeah, now we are comparing two different gas standards, right? We are comparing volume in milliliters, but in two different gas standards. 500, it's BTPS on the ventilator, but let's say, and I assume in this example that our analyzer is set to ATP, actual temperature and pressure, and then we have quite off measurements here, right? So here explained again, we have a setting of 560 milliliters on the ventilator. However, but we know because it's in BTPS, it's going to under-deliver, right, in volume. And because there is no change of the gas conditions, the same amount of volume is then going to arrive at our analyzer. And again, if that analyzer is then set to ATP, it's going to measure the 500 milliliters that actually goes through the flow channel here and ends up at the test lung. So comparing means comparing, as you can see now on the slide here, comparing flow rates or volumes in different gas standards can lead to significant errors in your measurements. So how do we tackle that in gas flow analyzers? Well, that's why we have different gas standards we can set up on our gas flow analyzers. And the only thing you need to remember from all that is that your gas standard of your analyzer must match the gas standard used by your device under test. Yes. No, that's why. Unfortunately not. That's why we have, you will see on ventilators, usually you have a whole selection of different gas standards. The most common ones are BTPS and STP. That's different standardization on different temperature and pressure and humidity. The only thing is really you need to figure out what your device under test uses. In most cases, it's going to be BTPS, but again, it can be different. Usually, they specify that somewhere in service manuals or user manuals. If not, if you ask them, they should be able to give you that information. Sorry? BTPS, the main reason is because this is actually what ends up on a patient, but this is mainly for like ICU ventilations. So in some other applications, you probably might not have that amount of humidification, or you might not have a heated wire. Then you want to probably compensate differently for what's ending up at the patient. Yeah, and be aware that some ventilators even differentiate if you are in service mode, for example. Then there is a switch you can set no humidification, and then that changes actually the gas standard they are using. So this is really something you have to figure out. Yeah, but most important, really key takeaway is it needs to match your device under test. Otherwise, you can easily have like 15–20% failures. Yeah. So when we have the same gas standard that is used on our ventilator and displayed on our ventilator, and then also on our analyzer, then it should match what is being displayed, even though actually the devices measure a lower volume, but then we have the same gas standard displayed, and then it should match with our volumes, because we are now comparing apples with apples, or maybe these guys bananas with bananas. All right. Any questions about gas type and gas standard? So key takeaways, yeah?
I don't know if you would know this. From the anesthesia machine, you can turn on a heater.
Yep.
Now, turning on a heater, does that change
Not necessarily. Could be, yeah. I don't know by heart, but I can figure that out for you. Yeah, mind ray service manuals are pretty good actually. So I'm pretty sure we'll find that information in there. Yeah. All right, so again, key takeaways is make sure that your gas type is set up correctly. So if you measure air, make sure that it's not set to CO2 or something like that. And then, if even more important, gas standard needs to match their device under test. Okay, let's go on with the next settings. That's called trigger settings. Okay, so gas type and gas standard is important for measurement of flow and volume. Trigger settings are used by gas flow analyzers to measure the so-called breath-based parameters, such as the tidal volume, inspiratory and expiratory tidal volume, a respiratory rate, I to E ratio, and a P, for example. These are all parameters that somehow depend on the breath phases, right? So here are typical ventilation waveforms for pressure and flow. And while this ventilation is going on through your gas flow analyzer, it of course can measure flow and all the time. But if we want to know, okay, what was my inspiratory tidal volume? Means how much volume went to my patient in the inspiratory phase, and then how much volume came back, for example, or what was the frequency of that ventilation? Then somehow our gas flow analyzer needs to know, okay, what is an inspiration phase, what is an exhalation phase, and when does the next inspiration phase start? And we do that through trigger settings. So you will hear terms as like start trigger and stop, or sometimes also called end trigger. And this relates to the inspiration phase. So the start trigger marks the start of an inspiration phase, and the stop trigger then marks the end of the inspiration phase, which is also the transition to exhalation. And then the next start trigger means, oh, okay, the next breath phase actually starts. And if we know that in our gas flow analyzers, then we can calculate all the different things. You can integrate the flow over that inspiration time and say, okay, that's our inspiration tidal volume, right? Same for exhalation. So in order to measure all these breath-based parameters, your analyzer needs to be able to trigger. If it's not triggering, then you typically see like just dashes measured on your screen, or some ventilators have something, they display something called no trick or something like that. And also, most gas flow analyzers have some kind of an indicator on the screen that tells you when it's triggering. For example, with our ones, it's like a T that is flashing up on the display each time when it's detecting a trigger. So if you don't see that happening, if you don't have, again, a measurement of these breath-based parameters, then that means your gas flow analyzer is not triggering. All right. So again, we need triggering to be able to measure all these parameters. So, but even if, oh yeah, one last remark here, the term trigger settings, you will also see that on your ventilator. But be aware that this is something completely different. Has nothing in common. The trigger settings on a ventilator actually is there to set the sensitivity for the ventilator to trigger spontaneous breathing of the patient. So if the patient tries to inhale, then okay, if that flow reaches like 2 liters per minute or if I have a negative or pressure drop of 1 centimeter, then I want to trigger supported breath by the ventilator. So this is really not to be confused. Some people call us and say, hey, my trigger settings on the ventilator are like this. Does that relate to trigger settings on my analyzer? Not at all. It's something completely different. Okay, so even if our analyzer is triggering, so that's the first thing we needed to trigger, but even if it's triggering, if we have insufficient trigger settings, that's going to have impact on the accuracy of our measurements. So ideally, we want to have our trigger settings as close as possible to the reality, right? So in this flow waveform here, you see it's 0 and then suddenly it starts increasing and then it goes back and then to 0 and then suddenly it goes negative. So this is actually from here to here exactly is our inspiration phase. There, ideally, we want to have our trigger settings or triggers of our gas flow analyzer. if, like in this example, our triggers are a little bit delayed in time, then this has an effect on the accuracy, for example, on the VTI calculation. Because mathematically, what the device is doing is, when the start trigger hits, then it starts integrating, means some kind of summing up this flow that runs through the device until it's being triggered with the end trigger, so that the inspiration time is over. And in this example here, you see, because the trigger settings are not that close to the reality, we're going to miss a part here for our VTI calculation. And then even worse, because here our flow goes negative, and we count a part of the exhalation to our inspiration volume calculation. This is going to be counted negative. So in this specific case, our measured VTI is going to be significantly lower than our reality. Okay, so we want to make sure that we have as accurate triggering as possible. So before we talk about how we can ensure that and how we can find suitable trigger settings, let's talk about what are the trigger settings, or what are the parameters that we need to tell the device. So trigger settings actually consist of three main parameters. First one is a trigger source, then a trigger signal, and a trigger level. So trigger source defines the physical interface for the trigger. So this could, for example, be our flow channel of our gas flow analyzers, or a pressure port of our gas flow analyzer. And all gas flow analyzers out there, or at least all the ones I've seen so far, also have an external trigger interface, so that you can, some ventilators offer that they have a digital TTL signal that they actually trigger whenever they trigger the breath, and then you can connect that to your gas flow analyzer, and then that triggers actually your gas flow analyzer. Not happening very often, but some ventilator manufacturers have that. Typically, you have your flow measurement or pressure measurement, and then in the trigger signal, you need to define which signal should be used for triggering. Typically, it's flow or pressure. Okay, and then the trigger level finally defines on our curve, on our waveform that we selected, at what threshold should the trigger be activated. And beside the actual threshold value, we also have to specify should it be triggered when we are on a rising edge of our signal or a falling edge of our signal. Okay, does that make sense? Okay, so what is a good trigger signal? So the first challenge, if we have to take a look at triggers, is we need to find a suitable trigger signal. So what is a good trigger signal? Well, a good trigger signal allows us to set trigger levels as close as possible to the reality. So if we can have our triggers as close as possible to our real breath transitions, then that means our device can measure the breath-based parameters as accurately as possible. Right? Does that make sense? Okay, so what does that mean specifically? So let's have a look at the couple of three different signals and judge them for their qualification as a trigger signal. So this is the first one. The gray vertical dashed lines here indicate the actual real breath phase transitions. So here is where an inspiratory phase starts, here is where the expiratory phase starts. So the time in between would be our real inspiration phase. And this gray area here around the zero of this flow curve indicates an area where we don't want to have our trigger levels, because they are so close to zero. If you have a little bit of signal noise, you could have false triggering. So who thinks that this is a good trigger signal? Raise your hand, please. Okay. Who thinks it's a bad trigger signal? Okay. Okay. So let's have a look at it together. So you're not quite sure, right? Turns out that it is actually not that good. One part is very good, the start, right? Because here at the start, we have a very rapidly increasing curve or waveform. So that makes it easy for us to set a start trigger on a level that is quite close to our gray area we want to avoid, on a positive edge. And then see that dotted line here? I mean, my trigger here is very, very close to the reality. So that's very good, right? That's exactly what we want. But then the problem with this signal is at this transition here, it's not that good, right? The changes are marginal here in my flow waveform, and it's all within this area I can't really sufficiently trigger, right? So if I would set it to the same level as my start trigger, but on a falling edge, then my stop of the inspiration phase would be far too early, right? And my analyzer detected inspiration phase would be far shorter than the reality, and this is going to have impact on all my breath-based parameters measurement. Okay, so again, this is not a good one. The start is very good, so 50% very good, 50% it's bad. All right, second example, how about this one? Better? Yeah, definitely going to be better, right? Because now here we have a positive flow in the inspiration phase and a negative flow in the exhalation phase. We have quite steep slopes here at both breath phase transitions, right? By the way, this is very typical for a ventilation testing application, right? You have positive flow and negative flow through your analyzer. Yeah, so let's have a look. Here we can set our triggers on a rising edge here, right above our gray area for the start trigger. And then because here it goes negative, we can go like on a negative value on a falling edge. And our analyzer detected inspiration phase is very, very close to our reality, right? However, a little drawback here is, as you can see, it's all shifted a little bit in timing. So this means that our timing-based parameters like a frequency or a I/E ratio will still be accurate because it's just a little bit delayed, but overall it's still the same, pretty much the same, right? But beware that situations like this, we have the same little problem that we discussed in our first slide with the trigger settings that were a little bit off, right? So here in the volume is the area underneath the curve here on the waveform. Here we are missing a little bit of volume, and here we are counting a little bit of our expiratory phase as inspiratory tidal volume. So it is a good trigger signal, but it would be even better if we had a little bit steeper slopes of our signal here. Then even our tidal volume calculation could be more accurate. Last example, how about this one? This is the other extreme, right? This is perfect. This allows you very easily to set trigger settings that are perfectly in sync with reality. So lesson learned here, if we have to select the trigger signal, it has to have steep rising and falling edges at both transitions of our breath phase. Okay? So now again, that was a lot of information, right? And this is all background or like background knowledge. Yeah, question? Very good question. Yeah. So now, very good question. And now let me ask you that. So the ones of you that are involved in ventilator testing, have you ever had to touch the trigger settings of your gas flow analyzer? Raise your hand. No. Okay, that doesn't really surprise me because typically when you have gas flow measurement and you test a ventilator, typically you have flow and pressure waveforms that look somehow like this. So on the left-hand side, we have typical waveforms for pressure-controlled ventilation, so where the ventilator is controlling the pressure here in inspiratory time. And on the right-hand side, volume-controlled ventilation. And the nice thing about this is that in both cases, you see typically you have exactly these very steep falling and rising edges of your signal, of your flow signal in both examples. And the other nice thing is that your zero baseline of flow is usually zero. So at the beginning of your inspiratory phase, you have a rapidly rising flow in positive direction. And at the beginning of the exhalation phase, it crosses the zero line and goes negative, right? And because of that, all gas flow analyzers out there, they have default trigger settings which are exactly based on that. Okay, that's the good news. So they work in 99, I would say 95, let's say 95% of your applications, as long as you have a positive and negative flow through your gas flow analyzer. Some analyzers you will see they have different settings, sets, like presets for adult, pediatric, and high frequency. But if you have these set up in most applications, you just switch it on and see, oh yeah, it's triggering, and most likely it's going to work. Because the default trigger settings of your analyzer, of all the ones I've seen so far, are usually on the flow signal, for the reasons we just discussed. And the start trigger is going to be on a low positive flow through the flow channel on the rising edge of the signal, and the stop trigger is going to be on a low negative number, like -3, for example, on a falling edge. Some maybe you will see like 2 liters per minute, some 5. It doesn't really matter because this signal is so steep here. Imagine if it's a little bit higher or lower, it doesn't really matter, right? So that's the good news. So, and this means, as we've seen earlier in the slide before, these settings work independent from what my pressure is here of my ventilator, my setting, or independent of my flow, of my volume setting, because you always have this curves around the zero baseline and you have the steep falling and rising edges. This is really good. So the question is, what happens if that's not the case, right? So let's have a look at one situation just for your background knowledge, that if you should come to such kind of situation, that you know how to react. Okay, so this is an example of a ventilator which is in a BiPAP mode, and in this setup we have a leakage at the test lung. So here is our analyzer, here's our test lung, and in this setup, let's consider we have a leakage here that simulates a typical non-invasive patient interface, a mask with a leak, for example. So in this example, ventilator is going to apply pressure, there's going to be volume filling up the test lung, and then it's going to release pressure, and the volume actually goes out the leakage here and is not going back through our analyzer. So that means the flow through our analyzer is never going to be negative, and that means, unfortunately, that our previously discussed default trigger settings are no longer going to work. Okay, can happen that you get into such a situation. And if you look at the different pressure and flow waveforms for this example, then you see the flow waveform is not really sufficient for triggering due to the lack of a steep falling or rising edge here. On the other hand, here we see that our pressure signal is actually pretty good, right? So in such a situation, we would typically use the pressure signal to trigger. In BiPAP ventilation, our upper pressure limit is called IPAP and our lower pressure limit is called EPAP. And typically we would then set the trigger level for the start trigger at level of EPAP plus 1 centimeters of water, and a stop trigger on the falling edge on IPAP minus 1 centimeter of water. And that would work perfectly fine. The problem here is that your trigger settings are no longer independent of the settings of your analyzer. Because let's consider we have the first setting that we need to test in our service procedure is IPAP of 6 and EPAP of 2. So our levels would be at 3 and 5 to trigger. And let's assume the next setting set we need to test is IPAP of 8 and EPAP of 4. As soon as I apply these settings on my ventilator, my gas flow analyzer is going to go, oop, no longer measuring any breath-based parameters, because it's no longer able to trigger. Okay, and why this becomes obvious when we have a look at the updated graphics, our start trigger level that was based on our previous settings is now so low that it's never gonna be reached anymore. So it can't trigger anymore. So what we would have to do here is amend our trigger setting levels to the new situation of our ventilator settings, and then it would work again. Okay, so to summarize here, in most applications, as long as you have positive and negative flow through your analyzer, your default trigger settings would typically work. But if not, it's crucial that you understand how you can find the right trigger settings for your specific application. Any questions about trigger settings? All right, two more terms you might hear. They're not used very often, but just for in sake of being complete here, there's also a setting called trigger delay. This can be used if you have like signal spikes above your trigger level and you don't want to consider them as triggers. Then you can set a trigger delay, and this specifies for how long the trigger condition needs to be true until it's really considered as an actual trigger. Okay, so it is kind of important in high frequency ventilation, for example. So if you have like your default settings and the delay is a little bit too long, and then you might miss some pulses in your high frequency ventilation that you're measuring. And the second one is called base flow. With the base flow, you can define a flow offset that should not be considered in our VTI and VTE calculation. So this could be important if you have a setting where you have a leakage that is being compensated with a base flow by your ventilator. And then you could tell the device, oh, this is my base flow, and this should not be considered in my tidal volume calculations. Okay. Last thing about settings are the measurement parameters, right? You know, on your gas flow analyzer, you can set up your screens usually exactly how you want. You can configure what you want to see. And here it's important to know sometimes the terminology is different. So for example, one ventilator might use the term frequency for the respiratory rate. Another one, or your gas flow analyzer, may call it a rate, right? Or the maximum pressure during an inspiratory phase may be called P peak on one device, while another device may name it PIP for peak inspiratory phase. The exact same thing, but different naming, okay? So gas flow analyzers can typically measure up to like 25 different parameters. So it's important for our specific application that we ensure that we know the terminology, what are we looking at, and then also set it up correctly. And all the parameters typically can be also measured in different measures, a unit of measure, right? For example, pressure, typically on your gas flow analyzer, you can set it to be displayed in millibar, in centimeters of water, PSI, Pascal, whatever. So make sure that you have it set up as per your device under test. So you are comparing the right unit of measurements. Okay. All right, so that was about the challenge to have the correct settings for your application. So what are the opportunities opposed by these challenges? So first one I want to discuss with you is if you have a gas flow analyzer that supports or has that feature to save and use profiles, then it's highly recommended to do that. Because most modern gas flow analyzers allow you to all your settings. Let's say you have a specific ventilator, and then you talk to the ventilator manufacturer, you go through training, and you know, okay, this ventilator is using that gas standard, I have these gas types, these are the values and units I need to configure on my screens. Then you can save all that into a profile, and then next time when you have the same application, you can just load that profile, and all your settings and customizations of your screen are up to date and correct, right? So this helps really minimizing the risk of setup errors on your setting errors on your gas flow analyzer. And the second opportunity here is watch out for some advanced aids that your gas flow analyzer might offer. For example, latest gas flow analyzers usually have something like on-device waveform analysis. So you can have a look at your waveforms, and that's very helpful if you want to figure out trigger settings, right? And you can say, oh yeah, this is my waveform. It is around 0. We have steep falling and rising edges here. Here is a good level for my triggers, right? And if it comes to trigger settings, so some ventilator testers also give you some graphical information about, okay, what is it exactly that I'm setting up, and which curve which waveform am I triggering, flow or pressure, and on which edge of the signal. So this can be very helpful as well. And now back to the question, can that also be automated by the gas flow analyzer? The answer is yes. There are some state-of-the-art gas flow analyzers out there that do that automatically. So they, in real time, analyze the pressure and flow curve, and then figure out, okay, for this specific situation, these are the best trigger settings. So it takes a couple of breathing cycles, and then it figures out, yes, these are my correct settings, and it does that automatically for you. So imagine how helpful that is when your trigger settings are dependent on your settings on the ventilator, right? That saves you a lot of time. So yeah, all these features actually help finding the best possible trigger settings to make it possible to trigger as accurately as possible. All right, any questions so far before we talk about the last challenge? All right, so there are 10 minutes left, so let's go ahead with the last challenge. The last challenge we see often is that the test sequence and valid ranges defined by the manufacturers are sometimes quite challenging to understand. So here's an example, and don't worry if you can't read all of that. This is an example of a ventilator where we need to calibrate different pressure levels. So first at 0 pressure, then at 10, 20, and 30, or what is it, 10, 35, and 60 centimeters of order. And this is very typical, right? You have to set up different pressures on your ventilator, and then you have to measure whether or not these pressures are within a specific range with your analyzer. So it sounds really easy. Here, in this case, you see we need to do something at 0. We need to read some values, and then we need to set our ventilator to 10 centimeters of order, and then the challenge starts. We need to take some measurements, then we need to do some calculations here. We need to even calculate our lower limit and our upper limit, and we need to do that for each of the different scale points. So this ventilator manufacturer realized that this is quite complicated, so they added an appendix with a calculation example. I have detailed it for you. Per scale point, you need to go through 9 different steps of reading values on your analyzer and your ventilator, then calculate the valid ranges based on these readings, and then finally judge whether or not your calculated values are within a calculated range, right? So of course it's important that you are trained on the ventilators you are testing, but procedures like these can make it very cumbersome, right, and prone to errors, right? That's a Philips V60. Yeah.
It's got a whole page where basically you fill it all out and then you later do all the calculations.
Yes, yeah, exactly. But you have to do it yourself, right?
980, if you go to the
Oh, 980.
they give you an Excel spreadsheet that you just, it doesn't know where you.
Exactly. Yeah, exactly. And the 980, by the way, the 980 doesn't even specify exactly what. The 980 does, but the 840 does not. They have this automated calibration with one specific device, and everything else you have to figure it out yourself. Yeah. Yeah, exactly. I mean, calculation errors, transcription errors, interpretation errors, a lot, right? So this is very typical. There's another example here. This is from a neon Coden ventilator. Here it's about flow rates, but it's pretty much the same thing. It's just 6 steps instead of 9. But again, you have to do calculations. You have to calculate your limits yourself. And even take a look at this note. Yeah, if the flow is fluctuating, take the mean value of the flow. So that's also not that easy, right, on the fly. So pretty much the same situation here. A lot of manual steps, very difficult, right, to go through. The last opportunity that I want to present you here is something that not many gas flow analyzers have, but this is actually what our gas flow analyzers, for example, the latest ones have. And it's to use guided test sequence. We call them testing apps. So what these testing apps do is they guide you through the performance verification of the ventilator step by step by kind of mirroring the user manual in a guided procedure on the screen. And then they can take the measurements and interpret them automatically, because they know then, okay, for this ventilators, these are the values, and they can calculate the expected ranges because the measurement is already there on the on the device, right? Sometimes you need to key in something that you read on the ventilator then, and then it's doing the math, like the Excel spreadsheet you mentioned, and it can give you pass-fail results right there on the screen, okay? And then they can also store all these results and put it into a report at the end that you can then download from the device as a PDF file. So this helps, of course, to make testing workflows more efficient and also to eliminate the risk of reading errors like calculation errors and then also interpretation of these results. And additionally, because these applications are based on specific ventilators, we can also make sure that it loads automatically the correct settings for these ventilators. For example, the gas standard, gas type, and trigger settings. So it actually resolves all the challenges we have discussed in this session. All right. Any questions? Before we summarize, so the key takeaways from my point of view is, number one, ensure you understand your gas flow analyzer. Make sure that you study the manual and make sure you understand, for example, what is being measured in the main flow channel, and even more important, what is not being measured there. Where do you have to, for example, key in pressure or have an additional module for your oxygen or whatever. That's really important to make sure that you understand how your setup is going to look like. And then pay special attention to the setup, like the settings of your analyzer, that it matches what you want to measure actually, and your device under test. If there's one thing, again, I want you to remind from this session is the gas standard. This has by far the highest impact. Make sure that you know the gas standard used by your device under test, and then set the exact same gas standard on your analyzer. And last but not least, take advantage of your the advanced features that your gas flow analyzer, the current one or maybe the next one down the road, you're going to select, that you have these features that help you overcoming these challenges. There is support out there. I see too often that people just use it very old school, that they actually have the tools, but they don't really have the time to kind of learn it or to understand how it works. But it's really worth it. It's going to help you down the road for sure. It's an investment that's totally worth it from my perspective. All right, thank you so much. Of course, I'm here for any final questions. If not, it would be great if you could visit our table 28. Ooh, that's wrong here. It's table 28. Sorry, forgot to update that. This afternoon, yeah, it would be great. I'm gonna be there. I can show you how our devices can help you overcoming these challenges. And I have business cards here as well. If you want, please feel free to grab one. Don't hesitate to contact me, even if you don't use one of our devices. I'm really happy to help you with your challenges in the field. And is there any final questions? All right, I hope you enjoyed it and I hope you learned something new today, and have a great rest of your day. Thank you.